In this video, we are going to work on computing the volumes of various objects using disks and washers. And it'll become more clear what I mean when I say disks and washers in just a little bit. The main idea, again, is going to rely on integration. And in the last video, we computed the areas between curves by chopping up the areas into a bunch of little rectangles that we could compute the areas of individually, and then adding all of those up using integration, basically taking a limit as the number of rectangles goes to infinity and their size goes to 0, and we got exact answers. At the end of the day, integration is just adding a bunch of stuff up, and I mentioned it at the time. It doesn't have to be areas. In this case, it's going to be volumes. We are going to add up a bunch of little volumes to get one big volume. So, to do this, I want to just take a quick look at some geometric formulas for some objects that we know the volumes of, hopefully. So I want to think about, thank you, McAfee, volumes of, in this case, let's look at cylinders. And maybe like rectangular prisms. Let's start with these. And is that how you spell prisms? Maybe that's a Z. Prisms. I have no idea how to spell prisms, apparently. Okay, so we've got our cylinders and our rectangular prisms. For a cylinder, our shape looks like this. And you can imagine the back of the bottom that we can't see. I'm going to make the top and the bottom be circles of radius r, and I'm going to say that this distance right here is a height of h. And for this type of object, the volume is going to be equal to pi r squared times h. Essentially, all we need to do is take the area of the base, which is pi r squared, the area of the circular base, and multiply it by the height. For a rectangular prism, our shape is just a box. And again, I'll draw the backside that we can't see. And it has perhaps a width and what I'll call a length and a height along those three sides. And in this case, the volume is equal to the width times the length times the height. This one, again, though, if you think about it, is basically the same as this formula. If I find the area of just the base, which in this case is a rectangle, the area of the base is the width times the length, and then I'd take that area and multiply it by a height. So at the end of the day, for any of these shapes, which are what we call right cylinders and right prisms, where basically this thing is going up vertically at a right angle, this is going up vertically at a right angle, if that makes sense. Drawing in our little right angles on those two things, they go straight up and down. As long as we have a consistent thing there, we can measure our h in the appropriate way. Let me delete these just to not clutter these drawings. We have a similar formula. So in general, a right cylinder, prism, etc. has a volume given by whatever the area of the base is times the height. So you could have some generic weird shape on top, that same weird shape down on the bottom, and what we wind up with is, as long as this is a height and this surface here has an area of A, we wind up with the volume of A times H. So this is the formula that we're going to want to use. This is the disk that I'm thinking of using. Typically, we're going to be working with ones that do in fact have circular cross sections, so I'm going to be dealing with this formula. But this is the disk that I'm going to use to create my volumes. So if we want the volume of a more general object, and for now we'll stick to objects that have circular cross sections, and you'll see what I mean by that in a minute. So if we want the volume of a more general object, we can approximate it by basically splitting up the object, slicing it up into a bunch of cylinders. Slicing it up into a bunch of cylinders. So for example, if I'm dealing with an object that's like a sphere, so let's see how well I can draw this. Good enough. So here's my sphere that we're dealing with. And maybe for the sake of ease, I will put it on a set of axes here. Boy, that's looking wobbly. So here's my X, Y, and Z axis. Whoa. And maybe this radius of this thing out to the surface here is the distance of R. What we can essentially do is take slices of this, and I'm going to take slices parallel to the, in this case, the XZ axis. So we could slice through it right there, and we would get a slice that looks like basically just a circle, if you can imagine that. Hopefully that's clear. Draw some lines. This is sort of the surface that we just sliced through it in. And I can slice through it in that way a bunch of times to chop it up into a bunch of cylinders. So we basically wind up with an approximation that looks like the following. I'm not going to draw those lines, the axes in this one, just because it's going to be a little bit harder. So let's see how well I can do this. First, let me just start with a background color here to get the shape. Wanting it to be basically a sphere of the same size. But I'm going to create the sphere by basically slicing it up into a bunch of cylinders. And you can imagine, hopefully this drawing will make sense. We'll see how good of a job I can do here. That's good enough. And I'll come back the other way, and you can kind of see the other side of this thing. If you want, take a look in the textbook. Their picture is probably a little better than my hastily hand-drawn one here. But again, these would be kind of the flat surfaces. If I shade it, it'll make a little more sense. That we just sort of sliced this thing into. So those are sort of the flat faces. And I'll really shade this, make it an art class. Don't worry, I won't count you off down the line if you have to draw pictures like this, which you won't. But when you have to draw pictures on exams, just draw them as best you can. So hopefully that's semi-clear. I basically am taking a bunch of cylinders and using them to approximate this big sphere. And if this picture doesn't make sense, because I'm not very good at drawing with this tablet, take a look in your ebook. They have a much better picture of something along these lines. But basically, all I'm going to do is to, let me erase this a little bit, just because I made it so much worse. All I'm going to do is try to find the areas of each of these faces. So this face right here has an area of A, and here's our H, our little thickness of each cylinder. And that one little cylinder right there, maybe I'll make it in blue. Here's one little cylinder that we're using. There's one of them. That one little cylinder has a volume of A times H. And then we would do the same thing for the next cylinder, and the next cylinder, and the next cylinder, and the next cylinder, and add up to get our approximation. So in this case, we've chopped it up into, well, how many did I do? It looks like 5 cylinders. So in this case, N equals 5 cylinders. Okay. So what this means is formalizing this, putting this to use with a formula that we're going to be able to apply calculus to, is that if we have a solid object, I'll call it S for solid, so if S is a solid object that lies between 2 x coordinates, lies between, let's say x equals A and x equals B. And if each one of the cross sections of the solid has an area of A, and in fact we can just write it as a function in this case. So, and if the cross sectional, the cross-sectional area of the solid is given by, so basically perpendicular to the x-axis. Just make that totally clear. At a given x value is A of x, so it might change as we look at different cross sections, just like the one that we just did right here. Obviously this cross section, when we slice through for this cylinder, is going to be different than the cross sectional area if we'd slice through at a different x coordinate, or in this case we did them along the y-axis, so y coordinate. But that's kind of the idea. If we have a formula that tells us what that cross sectional area is going to be at a given x coordinate, with A of x continuous, so there's not any weird jumps, we have a normally shaped object, then the volume of S. So this is a really big, long definition that represents a fairly straightforward idea, hopefully, is as follows. This volume is, S is going to be approximately the sum of all those cylinders. So we're going to go from I equals 1 up to N of A of X of I star times our delta X. And this is basically the exact same thing we did before. This is now our area, and this is a thickness or a height. And when you multiply an area times its thickness, you will get a volume, so the units are appropriate. And if we want to make this exact, then we can apply a limit and let the number of these go to infinity. So the limit as n goes to infinity of the sum from I equals 1 to n of A sub xi star delta x. And again, the xi star just means, right, we're slicing this object up and sampling points in each of the slices that we took. So this is what it becomes when we take the limit, where we just need to remember that that delta x is going to get smaller as n gets larger, so it's going to be b minus a over n again. And this is our limit definition of an integral. So the integral from a to b of, in this case, a of x dx. And this is how we can find volumes. So I think this is easier to understand if we actually do a quick example. So let me do this one. Let's pick an object that we know the volume of, or that we can look up on Wikipedia or something like that if you don't remember, if you're not good with your geometric formulas that you probably had to memorize in high school. But let's verify the volume of a cone. So I want to verify the area, I said area, I meant volume. Verify that the volume of a right circular cone is V equals, hopefully you remember this, or at least once I write it, it's 1/3 pi r squared h. So basically it's 1/3 of the volume of a cylinder that kind of would take up that same space. So in this case, let me draw the picture of the cone that we're dealing with. I'm talking about a cone that looks like this. Where that's sort of the central axis of it here. Goes off this way, there's the radius, and this distance here is what we're calling the height. So this is the shape. I'm going to reorient this so that we can actually put it on a set of axes and come up with a formula for this a of x piece that we're interested in. So the way that I'm going to do that is as follows. I'm going to draw it this way. Let me put my y-axis here, my x-axis here, and I'm going to reorient this cone this way. So here is that exact same cone. So I want to pick out now a few important points on this. We made the tip of the cone be basically the origin, and so I want to think about some other points here. So this x coordinate right at the top of our cone, which is now the right end of our cone, this point right here is x equals h. The distance of the radius at this point right here, this is has a height of y equals r at that particular point. And so we have that point. It's basically the point h comma r, h in the x direction, r in the y direction, that's on that thing. And we want to slice this up at any arbitrary x value of our choosing, not just here at the end. So if I sliced it here somewhere in the middle, I want to figure out, undo that. I want to be able to figure out what this particular area is. So of this particular cross section, here is some x coordinate. I want to figure out what the a of x is for this particular slice. And that's just done at an arbitrary x value. So pick an x value, we should be able to figure out the area. So in this case, I'm recognizing that each one of these slices is a circle, and it's pretty easy to figure out what the area of a circle is as long as I know the radius. And so that's what we need to figure out for this one. What is that radius? It's not r. R is reserved to be the full radius of the base. This is going to be clearly less than r, so I'm writing it as rad instead, just so we don't get confused. Okay, so what do we know? We know that the area in general is going to be pi r squared, where this r is not necessarily this r that we're using over here. It's the r, the radius that I'm using right there. So maybe to make this slightly less confusing, no, this will be good. So what I'm going to do is write it this way. The area is equal to pi r squared for a circle. But what I want is the radius at this particular circle has a height that's just equal to the y value of, essentially, if you treat this as a line. So forget about this picture being in 3D. Let's just think about what this thing looks like straight from the side. So a equals pi y squared for our picture. So r is in general when we're talking about the radius, but for us the radius is just the height from the x-axis up to basically this line. So I'm just going to draw a straight on side view of this thing. I don't even care about the bottom of it. This is what we're looking at. We have the x coordinate, the y coordinate. I know this distance is h. I know this distance is r. And I want to be able to pick a specific point and go up and figure out what is this y value at any given slice that we want to use. So the idea is that this edge right here, I'm drawing in blue now, is a line. And if we can figure out the equation of that line, it'll give me the height, the y value, at any given x value. So this thing is a line, and the equation of our line is going to be some sort of y equals mx plus b. And this is our slope. Whoa. Well, that almost drew a really nice triangle unintentionally. So there's a slope. This is our y-intercept. These are the two pieces that I know. Just by observation, what is our y-intercept? Where does this blue line cross the y-axis? It crosses it at the origin. So that b, I know right off the bat, is going to be 0. So all I really need to figure out is the slope. The slope is the rise over run, you might recall. And in this case, if I pick this other point over here that is also on the line, and I pick this point here, I can figure out what the slope is by looking at the total change in the rise from here to here, and the total change in the run from here to here. So what's the delta y over the delta x as I go between those 2 points? Well, the delta y is how much the height increases. It goes from a height of 0 up to a height of r. So we've got r on top. There's our rise. Over the run. The run goes from 0 in the x direction to h in the x direction. Make that clear that that is the x-axis. So it's r over h. That is our slope. So I can see that for us, our y value is equal to rx over h, or r over h times x, however you want to think about it. And what this means is that our area of our circular cross-section at any given x of our choosing is a of x equals pi times the radius squared, right? Because it's a circular cross-section. So pi times the radius is just the y value, right? This is the height. Just to make it totally clear, the line that I drew in blue here is basically the same as the line in blue that I'm drawing on the cylinder up here. The radius at any given x value is tiny over here. It gets bigger and bigger. This is the equation that tells us exactly how that radius gets bigger. Using the maximum radius of the cylinder, or sorry, of the cone, and the height of the cone, we can figure out the ratio and figure out basically an equation for this line, this bounding curve. And that's all we've done. So the y value is the radius. It's just the distance perpendicular from the x-axis. And in this case, that radius, oops, wrong color, that radius is rx over h squared. So we need to square the radius. So that's what our formula is in this particular case for our area. This means that our volume for the cone is, again, integral from a to b, a of x, dx, right? This is the same formula that I'm just copying that we derived up here. But a and b represent our starting and ending points, and in this particular case, this thing is starting, we can see very clearly in our picture, it's starting at 0 and going up to h in the x direction. So for us, it's the integral from 0 to h of a of x, which we already found right over here, of pi times rx over h quantity squared dx. So as far as we're concerned, the pi, the r, and the h, these are just numbers. They're constants. And I can evaluate this square, pull those constants out of our integral, compute the integral, and get our answer. So that's what I'm going to do. If I square this whole term here, I'll wind up with r squared x squared over h squared, and I'll have, again, the integral from 0 to h of, let's move them all outside here, so let me give myself a little extra room. So I'll have the pi r squared over h squared. So I've moved this out, this term out, and this term out with this square. And all that's left inside is x squared dx. Hopefully we can integrate x squared. The integral of x squared is going to be 1/3 x cubed. So we've got pi times r squared over h squared times 1/3 x cubed, and that's being evaluated between 0 and h. When I plug in the lower bound of 0, this is all multiplication, it's going to give me no result. It's going to give me a 0 for my result, rather. So I really only care about plugging in the upper bound in this case. When I plug in that upper bound, I'm going to get pi r squared over h squared times 1/3 h cubed. And we'll simplify, do some cancellation. That h squared is going to cancel with 2 of the h's that we've got here. And cleaning this up, I'll be left with a pi, an r squared over 3, and an h. And that is the exact formula that we set out to prove over here. I guess I can rewrite it to look more exact. 1/3 pi r squared h. So there's the formula. So hopefully that gives you a sense that this process is actually going to work. We verified it on at least one thing. And in truth, it works in general. It hopefully makes some intuitive sense why this should be working. So basically, we're going to be able to deal with or apply this approach to anything that has a circular cross-section, and we're going to apply it in the exact same way. If we think about the solid that we're trying to find the volume of as being an object that's created by taking a curve and spinning it around an axis or revolving it around an axis, we can find volumes of those types of shapes. So basically, I want to find volumes of solids that are created by rotation. So solids built from curves of rotation. That is a very long, clunky way of saying this, that hopefully it makes sense. So let me just, again, do an example. Imagine that we've got the curve that we're interested in is the square root curve. So it goes like this. this is y equals the square root of x. And maybe I want to find the volume of the shape you would get if you took this up to 2, so from 1 to 2, here's my x-axis, my y-axis, and I rotated everything around the x-axis. So I spun this thing around. If we spin it around, we'd wind up with something that looks like this. So it would go up, be the same curve that way, it'd go down, and it would have a circular cross section. And let me just trim off the excess that we've got there and there. This is the volume that we've got. It's sort of a what we call a paraboloid, tilted on its side. And again, this goes to a distance of 2. Here's 1 in between. And this bounding curve, again, is y equals the square root of x. And if I want to find the volume of this, all I need to do is figure out a formula for the cross-sectional area. If I take an arbitrary slice of this shape at a given x value of my choosing, I need to be able to find that area. Again, we do it in the exact same way. The formula is going to be pi r squared, the formula for the area of a circle, and the radius is just going to be the y value, the height of the curve. That's going to be our easiest way to figure out the radius. And in this case, we have an equation that tells us what the y value is. The y value is equal to the square root of x. So this height right here is given by this formula. This is the radius that we're using. It is the distance from the axis that we're rotating around, the x-axis in this case, out to the curve itself. And then we're going to take a little thickness, slice this up into our disk, and this is the little cylinder, if you want to think about it like that, that we're using to approximate this one little slice. And then we're going to take a whole bunch of these slices and get our result that way. So in this case, we can compute this. We've got our y value. So if I come back here and I look at the equivalent picture back on the original curve, all I'm doing is basically taking a little rectangle. This height right here is the distance y. That thickness is our delta x. And we're going to rotate this thing around the x-axis. So we're taking that little rectangle and we're spinning it around to turn it into a coin, a disk. And that's what gives us the volumes that we're going to use. Okay, so our volume is going to be approximately, write this down here, oops. Our volume is approximately, well, all we do is sum up a bunch of these disks. So we take the area, multiply by our little thickness that we just said. This area is going to be pi times y squared, because y, again, is our radius up here. And that's going to give us the result. I'm going to leave off the indexes, the I equals 1 up to n, and just say sort of generically this is what it looks like. And after we apply our integrals and all that good stuff, so just sneaking that in there, this is really equal to pi times our y of x term squared times our delta x. That's what we're looking at when this is all said and done. So we apply our limit as n goes to infinity and turn this exact, and we get the following. That v is going to be equal to the integral from wherever we start to wherever we stop of our y of x quantity squared, don't forget my pi, times dx. And in this case, we were starting and stopping to get this shape. We're starting at the left-hand side at 0, and we're stopping when we get to x equals 2. So this is going from 0 to 2. The only thing we need to do is I can't actually evaluate this integral of a function y until I actually make it explicitly be in terms of x. So I need to actually plug in our actual formula. For us, the formula was that y is equal to the square root of x. That was the bounding curve that we're using, square root of x. So this is really the square root of x squared dx. There's the y. When we square the square root disappears, and we're just integrating from 0 to 2 pi x dx. And again, this is hopefully an integral that you can do fairly easily. We can pull that pi out. And the integral of x is going to be 1/2 x squared. And we're evaluating between 0 and 2. Again, when I plug in the lower bound of 0, I'm not going to get any contribution to the total here. So the upper bound's the only one that I'm going to care about. When I plug in a 2 here for x, I'll square it to get 4. I'll half that 4 to get back to 2, and we wind up with a volume of 2 pi. And I haven't written the units, but keep in mind this is a volume, so it's really whatever the units are cubed. So keep that in mind when we do this. Okay, so I think that one's good. Let's do another quick example to show you at the end of the last video in the previous section. The very last thing we did was we switched the orientation of the way that we were slicing up our, in that case, area from vertical slices to horizontal slices to show that that was sometimes easier. So I want to show the same thing in this case. So it may be easier close enough. All right. It may sometimes be easier to use horizontal slices instead of vertical slices. So let's take a look at that. I want to find the volume of this in this case. Let's see. Find the volume of the solid bounded by, let's say, y equals 2x squared. And we're going to rotate that around the y-axis. So 2x squared rotated about the y-axis from maybe y equals 0 to y equals 2 in this case. So y equals 2x squared, if I were to draw that, that is a parabola. It's a fairly steep parabola. It goes up like this in both directions. And so if I picked, for example, a distance of 1 here, if this is 1, and I plugged in the x value of 1 in, I'd square that 1 to get 1, multiply by 2, and I'd be up here at a height of 2. And then we're going to rotate it around the y-axis. So the y-axis is up here. We are rotating it around the y-axis. Here's our x-axis over here. And we wind up with a shape that looks like this. Let me draw a slightly better cross-section. Slightly better. Okay. So it actually looks the exact same. It's a little slightly different shape, but it's almost the exact same as the shape that we just did in the previous problem, but it's oriented vertically instead of down on its side. In this case, we can compute the volume doing essentially the same thing we did before, but now instead of taking vertical slices, it's going to be a lot easier to take little horizontal slices and rotate those around. To have that be our little slice of area that we're cutting into. So in this case, what that means is our thickness is now delta y. It's a little change in the y direction, not the x direction. And our radius, instead of being determined by the y value like it was in the previous example, the radius is now determined as the distance from the y-axis, which is going to be the x-coordinate. So in this case, the thickness is our delta y, and the radius is going to be the x distance, the x-coordinate, the distance from the y-axis, which is the x-coordinate. So we're going to need to use that thickness and radius to find the volume of our little disk. So in this case, the volume will again be pi times the radius squared, which is going to be some x of y potentially. It's the x coordinate squared times the delta y, and we're going to sum all those up. Sneak that sum symbol in there a little better. There we go. So again, here's our now a of y times delta y. Our radius now is a function of y, and therefore our area is going to be written as a function of y. And we can go through the exact same procedure. Take the limit as n goes to infinity, change it from an approximation to something that's exact. And what we're going to wind up with is having our integral the volume becomes an integral where we're going to use dy. We're going to integrate with respect to y because dy, there's our little bit of thickness. It plays the same role as the delta y in our approximation. And the area we said is x, whatever x is as a function of y. Right, so I need to rewrite this in terms of x as a function of y. So we're going to have pi times the radius squared, but the radius is x of y squared. And the bounds in the y direction that we're integrating from are from the origin 0 up to a height of 2 as the top. So from 0 up to 2. Again, these bounds need to go with whatever variable we're integrating with respect to. They're bounds in the y direction. So this means that we're going to also have to solve our x of y to be a function of y. And that means, this means that we need our y equals 2x squared, which is our bounding curve. We need to solve that for the x. So if I solve that for the x, I divide both sides by 2, and I'll take the square root, and I'll get that x is going to be equal to, in this case, plus or minus the square root of x over 2. And we can pick either one. Obviously, I'm just going to use the positive one because it's going to be easier. Our radius is measured from the center out, so from 0 out to this x, but I could have easily gone to the left instead and used the negative version, but there's no need to. Why make your life more complicated? So this integral down here becomes the integral from 0 to 2 of pi times our x function that we just found, which I'm going to use the square root of x over 2, that whole thing squared, dy. Sorry, I am a dummy. when I solved this, it was the square root of y over 2. Square root of y over 2. Kind of defeats the purpose of doing the problem in terms of y if you don't successfully solve for it. So back to here, I've solved for x in terms of y. This function is a function of y as I was expecting it to be. So we square the square root, pull out the pi. I'll have it over 2, integral from 0 to 2, and I'm just left with y dy. So that's what we're looking at for now. It's not too bad, another easy integral. The integral of that is going to be 1/2 y squared, because we're integrating with respect to y. So I have my pi over 2 times 1/2 y squared, evaluated for between 0 and 2. Put that in parentheses. And our end result here is we're going to wind up with a pi over 4 from this part. And we're going to be multiplying that by y squared, so 2 squared, which is going to be a 4. So we'll wind up with a pi over 4 times a 4, and the end result is just going to be pi, because again, the lower bound, the 0, isn't going to contribute anything. So we've got pi, and again, it's a volume, so whatever units we're using, units cubed. The last type of thing that's going to be important to recognize, so to quickly summarize, sometimes you're going to want to chop up your shape vertically. Sometimes you're going to want to chop it up horizontally, and that will determine whether your whole problem will be working with the variable x or with the variable y in your calculations. The other thing that we'll need to do, at the beginning of this we said we were approximating these volumes using disks and washers. So far we've only done disks. So what do I mean when I say a washer? When I talk about a washer, what I mean is, what if there's some hollowness to the shape? What if there's a hole carved out of the middle? So, in general, we have that our volume that we're trying to find is going to be pi times the integral from whatever bounds a to b times our radius squared, so pi r squared. That radius, I'll use a capital R here just to make it clear. This r of x would be y, and we're squaring it. This is in the case that we have our vertical slices, so that the y coordinate, the distance from the x-axis, is the radius of the shape. So basically, whenever your shape is generated by rotating a curve around the x-axis, the y-coordinate is going to be the distance from the x-axis. It's going to be the radius that we're going to wind up using. So these are our vertical slices. So these are for our vertical slice, rotation about the x-axis. Or similarly, we'll have that the volume could also be pi times the integral, and I'll just use two different letters, integral from c to d, of a radius that's a function of y squared dy, where this is just x, basically. It's what is the x distance from the y-axis, and this is it when we're using our horizontal slice for our shape, and that's typically done when we're rotating about the y-axis. So keep that in mind. These are our two formulas. At the end of the day, you don't really need to know both. You just need to know that it's pi times the radius squared. And if you just draw the picture, it'll be clear what the radius is. The radius is just the distance from whatever axis is being rotated about. So if you're rotating around the x-axis, the y-coordinate is the distance from the x-axis. If you're rotating about the y-axis, the x-coordinate is the distance from the y-axis. And it's pretty obvious once you draw the picture. So there's our disks, but what if we have, like I said a minute ago, what if there's a hole? So what if our shape is hollow? Let me do an example and we can kind of see how this is going to work to hopefully get this to all work out. So let's say we wanted to do something tricky here. Let me see here. Let's say we want to find the volume of the solid generated by rotating or rotation of the region bounded by, let's say, two curves. Y equals 2x squared and y equals 2, and maybe we're rotating them about y equals 3. Okay, so we aren't even rotating about an axis at this point, we're rotating around another line. If you want, in a little bit, I might refer back to these, and so I don't have to always write them out. I might call this one f of x, and this one can be g of x, just later on when we write this out, maybe in more generality. So let's draw the picture to understand what this means. The picture that I'm going to be looking at is the following. So this is a hard problem in a lot of ways. Here is my x and y axis. The first shape right here is a parabola that opens upward. So I have this opening upward, and we're chopping it off at y equals 2, at a height of 2. So here's the shape. This is the region that I'm interested in. And then we're going to be rotating it about this line, y equals 3. So here's the y equals 2x squared, here's y equals 3, here's y equals 2. We're rotating about this one, and what we're going to wind up with is basically little slices of this that are going to get rotated about this thing to create another image of the slice up here, and we basically get what I can only describe as a washer shape. So this is drawn very poorly, but hopefully you kind of get the sense. And we're rotating a bunch of these, so ultimately the shape that we're going to wind up with is something that looks vaguely like this. Hopefully this works. We're going to wind up with a shape that basically looks kind of like a donut, where the cross-section of our donut this hole inside the donut is like we cored out a straight cylinder, so it's flat on these two parts, and then the cross section is like a paraboloid cross section, or a parabola cross section rather. So hopefully that kind of makes some sense, that we've got this hollowed out donut shape where we've cored out the middle. That's the shape we're trying to find this volume of. So how would we do this? Well, how do you find the volume of this weird washer shape? So instead of using a disc, we're using a washer. How do you find the volume of that washer? So I'm calling this the washer shape. How do we find the volume of the washer? Well, basically, it's just a large disk with a smaller disk removed from it. So you can think of it as basically being, and hopefully a clearer picture, just imagine we had here's our initial disk. we can find the volume of that, but now I'm just cutting out another disk from that. So I'm going to remove a disk from a disk to get a washer. The way that we're going to do this is by treating this as the axis that we're rotating about, and I'm going to treat this inner distance as 1 radius, and then this outer distance, so that distance goes down to, this distance goes down to my inner radius, this distance goes down to my outer radius. I'm going to call the little inner one lowercase r, and the outer big one capital R. And so all we need to do is find that the volume is equal to the big pi r squared minus the little pi r squared. Right? This is the volume of the large disk, and this is the volume of the small disk. So the large one was the blue one, the small one was the red one. These are the lines that I'm referring to, the red and the blue. And we can clean this up a little bit by factoring that pi out, and we can really write this just as pi times the capital R. Maybe in this case it's a function of x up here at least. Right? And the way we've got it oriented here, you go to a different x position, you're going to get a different inner and outer radius. So r of x squared minus little r of x squared. That would assume, again, I've kind of changed the orientation. Let's pretend that this was the x-axis that we were talking about. Where these r's are just the distance from whatever capital R and lowercase r are the distance, not from an axis necessarily, but from whatever the, not from the x or y axis necessarily, but instead from the actual axis of rotation. So in this case, the axis of rotation up in our example was the line y equals 3. And that makes it a little bit trickier. So, how would we set up this problem? Once I have the volume of my little washer, which we've got here, all we have to do is integrate and add up all the different washers that are going to be used to make this donut shape that we've got here, our stack of washers. So let's keep that in mind. To set this up, we're looking at an integral that's going to be basically the following. All I need to know is what are my 2 radii. So for us, what is r of x and little r of x? Capital R of x, little r of x. So if I go back up to my picture, my outer radius is going to be the distance from y equals 3 to the parabola. The parabola is what dictates the outer radius. It's the further from the center. So that's going to be from y equals 3 down to the parabola, which is y equals 2x squared. So all we have to do is 3 minus 2x squared. That is our formula for that radius. That is the distance. For the little one, the little radius, it's the distance from the axis of rotation, which is y equals 3, down to this line, which is y equals 2. And that one happens to be constant. It's from y equals 3 to y equals 2, so it's just 3 minus 2, which is 1. And now that I've got those 2 pieces, our volume is going to be the integral of pi times the outer radius squared minus the inner radius squared. So pi times 3 minus 2x squared quantity squared minus the inner radius, which was just 1 quantity squared dx. And the last thing we need are our bounds of integration. To find that would be the techniques that we used before. I need to know where these 2 points of intersection occur. So where does y equal 2 intersect with y equals 2x squared? And by observation, if I set this and this equal to one another, so I get 2x squared is equal to 2, that must occur at x equals plus or minus 1. So I'm just setting those equal to each other to solve for plus or minus 1. So from -1 up to +1. And this is the integral that we would then solve to find the volume that we're looking for. Again, it's not hard. You'll have to FOIL this out, simplify some things, integrate, plug in some bounds. It'll be a little bit messy. You can cheat a little bit and use symmetry. If you look at this shape, you'll notice the red region that we shaded earlier is symmetric on the left and right. So instead of integrating from -1 all the way to 1, I could just integrate from 0 to 1 and then double the result to get the volume I'm looking for. And that would be kind of nice because, again, I'd much rather plug in a 0 as my lower bound in general than plugging in a number like -1 and having to worry about making an arithmetic error somewhere along the way. So when all that is said and done, I'll trust you to go through it. I did this earlier. Hopefully I didn't screw it up. I found the volume to be 48 pi over 5. 48 pi over 5. So hopefully you can come to that same thing if you work that calculation out yourself. In the next section, what we're going to look at is finding more volumes, but I'm going to give you a different technique that can sometimes be easier, sometimes be harder than this technique. So see you at the next video.